end behavior and zeros. When you look at polynomial functions and notice how it acts as inputs increase, 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 or decrease, 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 then you'll notice that away from the x-axis, there's a certain direction that polynomials go. There's actually 4 different possibilities of polynomials, all based on the degree and the leading coefficient. So, for an even degree function with a positive leading coefficient, the inputs keep increasing and the outputs will also increase. And as the inputs decrease, the outputs will still increase. These work for every single even degree function. So you could say that every single even degree function acts like a parabola for very large inputs. So as x goes to positive infinity, f of x goes to negative infinity, and as x goes to negative infinity, f of x also goes to negative infinity. Here we have, as the x decreases, or the input decreases, the output's also going to decrease. And as the input increases, the output will also increase. And so we get, as x goes to positive infinity, f of x goes to positive infinity. As x goes to negative infinity, f of x goes to negative infinity. And if we have a negative leading coefficient, then we'll get an end behavior like this, where the input decreases. This time, the output is actually increasing. And as the input increases, the output is decreasing. Let's talk about zeros. Zeros, solutions, roots, and x-intercepts are all inputs that produce 0. Imaginary roots, solutions, and zeros are indicated by a change in symmetry of a curve, but will not create an x-intercept. Here, you can see this curve is pretty smooth, and then something happens here and it doesn't look symmetric. There's no axis of symmetry here. And on this side, this also doesn't look symmetric. This means that for this function, it's not just a cube. It actually has more roots than a cube. It has 2 real, but it has some imaginary there too. Repeated zeros are represented by 1 root and 1 x-intercept, indicated by the curve touching the x-axis once, but not passing through it. Real root solutions and zeros are indicated by x-intercepts here and here. Even degree functions have at most the same number of zeros as its degree. So here we have a 4th degree function with 1, 2, 3, 4 roots, all real, all x-intercepts, and at least 0 real zeros, and that will not have any x-intercepts. It's going in the same direction, the end behavior increasing, 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 but there aren't any zeros that are real because there aren't any x-intercepts. Odd degree functions can also have at most the same number of real zeros as degree. Here, if we have a 5th degree function, a 5th degree function can have 1, 2, 3, 4, 5 real zeros. But a 5th degree function, or any odd degree function, has to have at least 1 root, because its end behavior implies that the graph must cross the x-axis at least once. The decreasing inputs make the output decrease, and the increasing inputs make the output increase. this would be 4 positive. And then imagine it flipped. We're still going to have some decrease and some increase in the end behavior. So it's going to have to cross at least once. Here we have a sketch of a cubic function with a positive leading coefficient and 3 x-intercepts. The max number of zeros, the number of x-intercepts, 3, the same. The end behavior follows the rules for a odd degree function with a positive leading coefficient, and therefore the number of n type of zeros, or 3 real zeros, indicated by the 3 x-intercepts. A 5th degree function with a negative leading coefficient and 4 roots. Max possible zeros, 5. Number of x-intercepts, 4, can't be more than the roots. The end behavior is going to be different than the one before, because for end behavior, the odd degree function with a negative leading coefficient looks like this. And the number and type of zeros will be 1 repeated, indicated by 1 less root than the degree, and then the rest can be real. So that leaves 3 reals, 4 roots. But let me show you how you can tell that this is actually a 5th degree picture, but only has 4 roots. Let's talk factors. This 0 is going to produce 1 factor. This 0 is going to produce another factor, and this 0 will produce a 3rd factor. But this 0 here, since it's repeated, actually will produce 2 factors. So we have 1, 2, 3, 4, 5 factors. 5 factors, 5 degrees. A 5th degree function with a negative leading coefficient and 4 roots, same as we've seen before in the description. We have to have 5 zeros. They can't have more than 4 x-intercepts. The end behavior has to be like this, because the end behavior for odd functions with negative leading coefficient is this. But the number and type of zeros can change a bit. What if we still keep the repeated, again, 4 roots, 5 degrees, we need 1 less counted root, or we need 1 root to count as, 2 roots to count as 1. But let's say we only have 1 real. We can still have 2 imaginary, remember? Imaginary roots must come in pairs. So this still adds up to 1, 2, 3, 4 roots, but let's see about the factors. 1 repeated, 2 factors of x. 1 real, 1 more factor of x. We're up to 3 now. And then 2 more imaginary means 2 more factors of x. 1, 2, 3, 4, 5 factors, 5 degrees. 6th degree function with a positive leading coefficient and 2 x-intercepts. Max possible zeros, 6. Number of x-intercepts, 2. And behavior, same for even degree functions with a positive leading coefficient. 2 real zeros, x-intercepts, which means the rest have to be imaginary. We might be able to get some repeated if we use some repeated. That's a possibility. But this is the simplest way to deal with a sketch like this. A quadratic function with a negative leading coefficient and 1 root. Max possible, 2 to match the degree of 2. The number of x-intercepts has to be 1 because there's only 1 root. The end behavior has to follow even degree functions with a negative leading coefficient, and that means that you're only going to have 1 repeated root. 1 root, 2 factors of x, a degree of 2. A 5th degree function with a positive leading coefficient is impossible. Remember before, when we talked about odd degree functions, odd degree functions have to cross the x-axis at least once because their end behavior is different. If you plug in a positive, that's going to cause a positive output for large positive outputs. For small negative inputs, that's going to be a negative input. Quartic function with a positive leading coefficient and 0 x-intercepts. This one is possible. Even degree functions can have 0 real zeros because their end behavior. Let's review. Zeros, roots, and solutions and x-intercepts are all inputs that produce 0. Imaginary roots, solutions, and zeros are indicated by a change in symmetry of a curve, but will not create x-intercepts. Also, they have to come in pairs. Repeated zeros represent one root and one x-intercept indicated by the curve touching the x-axis, but not passing through. Real roots, solutions, and zeros are indicated by x-intercepts. Even degree functions can have 0 real zeros and can have the same number of zeros as the degree, and really any number of zeros in between. Odd degree functions can also have the same number of zeros as the degree. It can have a less number of zeros than degree, but it has to have at least one zero because of the end behavior. It has to cross the x-axis. This is the end behavior for degree functions with a positive leading coefficient. Now for even degree functions with a negative leading coefficient. Odd degree functions with a positive leading coefficient. Odd degree functions with a negative leading coefficient.